So this is the second recording for this lecture on infrared and Raman spectrometry. So this here is just a quick kind of sketch of my fluorimeter. I can use fluorescence equipment to measure Raman. I've said that because I said that when I was talking about fluorescence, I said that I used Raman to calibrate the emission wavelength for my detector. If I kind of play this up a little bit though, get rid of my light source and my initial monochromator, replace that with a laser, then this is much more aligned to the traditional kind of Raman devices which are used in modern day spectroscopy. So we have a laser going in, so that is bright monochromatic light going in, so I don't need to select wavelength there. Goes into my sample, and at 90 degrees, just like in fluorescence, I have my emission wavelength coming out. There are variations on this theme. I'm specifically thinking about Raman microscopes. I don't talk about Raman microscopes, but Raman microscopes, they have the light coming in and they measure completely the backscatter, so they measure light at 180 degrees to the incident light. But we are always measuring away from the initial kind of direction in. Detectors for Raman's PMTs always, just for the sensitivity. Raman is a very, very low signal thing. So I keep on talking about scatter, but what actually is scatter? So here I've just got this molecule, and if I have incident light coming in, and that light is scattered, but there is no change in wavelength, that I refer to as Rayleigh light, Rayleigh scatter. We will always see Rayleigh scatter. It's something we see even in fluorimeters, and we can see Rayleigh scatter at twice and half the wavelength of my incident light. So it's something that we see in fluorescence quite a lot. There is no change in frequency. The reason I see it at twice and half is just because of some peculiarities of the optics. But Rayleigh, no change of incident, no change of energy of the incident light. But I also can have light which is inelastically scattered. And so that would be my Raman, where I have a change in frequency and my emitted light is of a slightly lower energy than my incident light. And I have a version where I can have my excident light being a slightly higher energy than my incident light. We see a change in frequency, and this change in frequency is related to the vibrational energy levels within my molecule. Now, something that's interesting about Raman, when we think about it, comparing it to infrared, is that I can use any wavelength of light. Because I'm looking at scattered light, I can use any laser, any bright light source that I like. I'm not just limited to having light sources down in my infrared region. But there's a benefit to being able to choose any wavelength of light, in that my intensity of my scatter varies with wavelength, varies with frequency. In fact, there is a frequency to the fourth relationship for my incident and my excident, my incident light and my excident amount of Raman scatter. This isn't a property of detectors being better in the visible, or, you know, it's nothing to do with the absorption of the medium or anything like that. This is just a genuine relationship between my incident of light and my excident light. So there are benefits to me having a green laser over a red laser. I see a lot more Raman scatter. And when I'm looking for one photon in a million, it becomes a whole lot easier if I start to all of a sudden be looking for 5 photons in a million. The other kind of real benefit for Raman over infrared is that I can do it in the solution phase. Raman light, because it's a higher, because I'm often looking at visible light to get my Raman scatter, it's not absorbed the same way as it would be if I was looking down in the infrared. So if I was in aqueous solution in the infrared, all I would see is a great big absorption from that OH vibration in the water. cannot do infrared in water. And if you've ever had a wet sample, you know very well, you can see nothing. That OH absorption, which is broad anyway on your infrared, all of a sudden it starts to mask all the peaks that you want. As soon as I'm in solution, I get nothing. Whereas Raman can tell me all sorts of information about solution. And I can take that further, not just looking in aqueous solution, but looking in vivo, looking into cells. Now, a friend of mine did some rather fun work using Raman. This is from the group in St Andrews, where they looked at, they combined some microfluidics and some Raman spectroscopy to look at whiskey. And this is a rather fun paper, but this was kind of one of those kind of just before Christmas, let's do something fun, on actually some quite serious work. They were looking at Raman from urine samples and being able to detect cancerous cells or precancerous cells in urine sample. So this is looking at bladder cancer, which is very, very difficult to detect. And this group, whilst they had this fun paper on whiskey, is using exactly the same techniques to be able to look at cancer. And we couldn't do that with infrared. We might know what we're looking for with infrared, but we can't see it because of the water. And drying it down and then all the other stuff that's in there as well. We just can't see what we want to be looking for with infrared. So Raman is a fantastic technique. And this is quite a fun kind of paper. I always like a fun paper for Christmas. So I've kind of given you some of the benefits of Raman over infrared, but I don't want you to think that it's one or the other. They combine really, really well. They give us slightly different information. Now I'm just going to kind of go into this Raman and Rayleigh scatter a little bit more. So here I just have my, I've got an S0 and an S1. They're both vibrationally ground state as well. And you can see I've got this V1, V2 level, and I've got this virtual level. This virtual level isn't actually an energy level. It's just that if we have this picture, we need to have our lights kind of scattering. We need to have something to help us understand the concept of scattering in light. Mathematically, I could go through this, but you don't need to understand the maths, you just need to understand the general principle. So here I have Rayleigh scattering. So Rayleigh scattering is the one on the left here. I see incident light coming in and out, same wavelength, no difference. Rayleigh, inelastic scattering. Sorry, elastic scattering. No, yeah, I was right first time. Inelastic scattering, no change of wavelength. Then we have my Raman and my Stokes and my anti-Stokes. So here my Stokes. I start in the ground vibrational state, and then I'm scattering from this virtual level, but I end up in a vibrationally excited state. And so I've got this change in frequency of light, and that's telling me something about this energy gap V0 to V1. And I can have anti-Stokes. If I start in a vibrationally excited level, I can end up down in the vibrationally ground state. Again, it's telling me the same piece of information, but this time the wavelength of light I see is a little bit shorter, the energy gap is a little bit higher. I've also indicated one other Raman here, which is when I actually excite all the way up into this S1 level. I essentially, my S1 is acting as a virtual level. I'm not absorbing and then re-emitting from it, so it's not like fluorescence or anything like that. It's just that the energy gap of this absorption happens to align with this energy gap S0 to S1. Now, there are benefits to me doing this. I'm not going to go into them now, but it's such an important thing. We actually have a name for it, which is resonance Raman. So we're in resonance with the actual absorption within the molecule in the first place. So this virtual state is a way that I explain Raman. It doesn't exist. It is entirely, as the kind of the name says, it's a virtual state. It can be at any wavelength I like. It's a continuum thing. And so I see this energy gap from my vibrational levels at the bottom. It has nothing to do with whatever this energy of this virtual level are. If I go back to the previous slide here, I see a lot more of this Stokes transition, this Raman Stokes, than this Raman anti-Stokes. So why is that? Well, it's just a simple one. If I've kind of got a figure of it here. So this is I've got my Rayleigh line in the middle, and then I've got these energy transitions. So these ones on the left-hand side, the negative energy transitions, these are my Stokes lines. The positive ones are my anti-Stokes lines. Well, what's the reason for that? Well, it's just simply at room temperature, most things tend to be in the ground vibrational state. We can do a Boltzmann calculation and work that out. But most of my molecules are in a ground vibrational state. Therefore, very few of them are in that excited state in the first place for them to kind of be able to lose energy by this Raman transition. I can encourage things to be in an excited vibrational state, and there is, again, a type of Raman which does that, but it's not an essential thing. I don't need to see the anti-Stokes, so I can get an awful lot of information just from the Stokes lines. So I've said that we use a laser going in. One of the side effects of using a laser is, not only is the light intense and monochromatic, it's also polarized. Does the polarization have any effect on the Raman? Well, we can look at the polarization ratio of the scattered light. So this is the ratio of the light which comes out perpendicular to the light that comes out plane parallel with the incident light. And what we find is that we can actually get a little bit more information about my molecule than I had before, in that if I have a symmetric vibrational mode, so this would be something like a benzene breathing or a carbon dioxide symmetric stretch, I find that these have a much lower polarization ratio than something which is an asymmetric vibration. So this would be a carbon dioxide having an asymmetric stretch. I'm just so you can picture me right now, I am actually doing the carbon dioxide dances for, the different things. Asymmetric vibrations show an increase in depolarization. I'm introducing this fact to you now. It's something that we can consider, and it's something that we might want to look at a lot more in understanding the shape and structure of a molecule, but I'm mentioning it rather than going into any great detail at this point. So, excuse me, just some practicalities about Raman. I've said before, the intensities are incredibly low. So that's why lasers are really important. I've said already that it didn't really come into its own until the 70s and 80s when lasers were much more common. But because of this, I can have a problem with the Rayleigh scatter saturating my detector. So I see a lot of Rayleigh light. You saw in that figure a couple of slides ago, my Rayleigh peak was way off the page, and that was intentionally drawn that way. Raman is a very, very low signal thing. So how do we stop this? How do we stop this incident wavelength saturating my detector, this inelastically scattered light saturating my detector? We use something called a notch filter, and a notch filter is just there to eliminate the same wavelength of light as goes in. It just is acting at that particular wavelength, or all wavelengths shorter. I've already said that higher frequency light gives better Raman signal, so it's better to use a red laser over an infrared laser, or a green or a blue laser. We have other problems though, there are benefits to going green, blue, UV, but there are also problems with going green, blue, UV. We might be hitting absorptions of the sample, which might be leading to problems with heating the sample, or damaging my sample in some other way. So you have to kind of think carefully and have a balance of the wavelength and the other consequences of having high energy light going into my sample. The other big problem with Raman is that I said that the spectrometers are very, very similar. I start to excite a sample. If I'm hitting it in its absorption band, I can see fluorescence. No, not I can see fluorescence, I will see fluorescence. And this can be a real problem for Raman spectrometers. And so we have to get a little bit clever. Raman is an instantaneous thing. Fluorescence, the thing lives in its excited state for a little while. So if I can time gate, if I can kind of stop light coming in after a certain point, then I'm going to stop the fluorescence, or stop most of the fluorescence happening. And so this is something that we can consider as well. So I'm just going to finish kind of lecture 2. I'll be back with slideshow 3 in just a minute.